the u's and p's were changing signs from u is equal to 0 to u equal to 0. So in Schwarzschild case, we know that branch point or branch cut type of thing which caused that sign change. So
in
the Schwarzschild cluster. But in Riddler case, this branch cut thing is not manifest.
What you mean? You're asking why is r equal to 0 not the same thing as r equal to 2m? So yeah, I mean, so okay, so let me. So the question is basically whether r equal to 0 in Minkowski, how is it different from r equal to 2m? Is essentially the question, right? R equal to 2m of Schwarzschild.
Basically, u equal to 0 is the branch part of that Schwarzschild thing.
Right. Yeah. So it's not so much that it is a branch cut. So what is happening in the case of Kruskal is that you are the definition for u and v, or let's say capital X and capital T, is basically valid only in some region. So for x greater than 0, or u greater than, I think it was u less than 0 and v greater than 0. So that's the only region where the definition that we had in terms of the exterior Schwarzschild applies. So the definition only gives you a definition for u less than 0, capital U less than 0, and capital V greater than 0. That's where the only definition exists. But then what we say is that we declare that u and v are real, are valued in the real line. So that's a declaration that we make. Okay. So when you start from, in the case of Reissner, for instance, what you are doing is you are starting from your Reissner coordinate system, and then you are going to let's say your standard Minkowski coordinate system where it is minus dt square and dr square. So your question is basically why is in r equal to 0, where you typically have a radial coordinate as positive real line, why are you not extending it to r less than 0? That's really your question. Okay, so the answer is, I mean, geometrically we kind of know that radial coordinate is radial coordinate, right? And the reason, sort of like if you want to really make it into a sort of like a formal argument, is that at r equal to 0, the sphere of Minkowski space shrinks to 0 size. So you cannot continue r to less than 0 because it will essentially be like extending two conic, let's say two cones attached at the tip. That's roughly the kind of structure that you will get. And because of this, at this point, you will not be able to put a chart. This point makes this structure, let's say these are cones, not a manifold. So you cannot do that when r equal to 0. So that's why r equal to 0 is a natural endpoint for the space-time in Minkowski space. But at r equal to 2m in Schwarzschild, the sphere is still finite size. Okay, the radius is 2m. So you can still continue. And that makes it more like a, that's why this idea that this is a wormhole exists, right, on two ends. So from one side to the other, if you take, so in the Kruskal picture, let's say this is your Kruskal singularity, and this is your past singularity, and so this is not a very good picture. So this sort of a picture, so this line here, once you suppress, the two sphere is suppressed here. So if you put the sphere back in, this is basically a wormhole. Okay, so that's why this is sometimes called the Schwarzschild wormhole, the Kruskal extension. So here there is no such wormhole, because if you try to do that, it will collapse to a point here. So, and this is not a, this is not a genuine, manifold. You cannot think of it as a space-time manifold. So that's sort of so I mean, physically, of course, we know that the radial coordinate is radial coordinate. So that's the reason why it's not another asymptotic region. Here, on the other hand, once you continue it, we know that we have gone into the black hole. But where is this coordinate going? So the only way to attribute that is another universe. You cannot think of it as the other side of the black hole or something, because it's not the same r coordinate. We are still inside the black hole. So this entire region, once you are, everything except this region is inside the black hole in some sense. Okay, so that's why this region is some other exterior region. Any other question? So yeah, so the sphere is very important in that discussion. The sphere collapses to 0 size at r equal to 0 in Minkowski space. That's the answer to your question. Your question is really not about Schwarzschild. It's about why don't we continue the radial coordinate in Minkowski space to negative directions. That's your real question. Okay? So anyway, and the answer is basically that the sphere collapses. Any other questions? Okay, so today what we'll do is we'll again have some kind of quasi overview. I mean, most of the things in this course, I mean, that is, you could teach this for a long time from various perspectives. So we are kind of trying to give you an overview of the general story to some extent. So what I'm going to tell you today is a general overview of black hole thermodynamics. Okay? So most of the things that we need from classical general relativity, we can sort of, you can sort of assume, or you can. It doesn't really affect much of our eventual discussion. So a lot of these stories you can sort of believe, and that's I'm not going to derive it in horrendous detail, but it should be sufficiently clear. Okay, so let me start with ordinary thermodynamics. So the non-trivial claim here is that black holes behave like thermodynamic objects. Okay, so that's the eventual non-trivial claim of today's lecture. So the starting point is that so the starting point is, of course, we want to first have like our standard formulas for thermodynamics. So let me just write that. I'm sure all of you know them very well, but I'll write it in a form which kind of lends itself to building the analogy with black holes. So I'm writing. You can add as many number of extensive quantities and their corresponding potentials. Okay, this is a standard thing in thermodynamics. I'm sure that you know is better than me. So this is the one that you probably see in thermodynamics, but there is nothing prevents you from adding things of this kind. The key feature about this is that this is an extensive quantity, and this is typically viewed as a potential. Okay, so here I'm calling this, in the case of black holes, this J will be an angular momentum, and omega will be an angular velocity. So usually we will attribute these quantities to the horizon of a black hole, especially if it is a rotating black hole. Okay, here. And here it is, if it is a charged black hole, the charge is again an extensive quantity. Okay, and the phi is the electric potential, if you like. Okay, so that's the general structure of your first law. So this is first law. And this is, at the moment, this is just a statement about thermodynamics. And then there is also second law, which says that delta S is greater than or equal to 0. In systems which are in any general system in nature. Here I have to restrict it. I have to say that this is when things are in equilibrium or quasi-static evolution, approximately in equilibrium. Okay, or approximately means infinitesimally slowly changing. So this is first law. First law and second law apply in different contexts. First of all, this is when it is in equilibrium, and this applies anywhere. So if it is greater than 0, it is not equilibrium. Okay, so these are two general statements, and what we will try to do is basically what we will try to do is to make connections between and this is energy, this is temperature, this is entropy, and these are various kinds of potentials and extensive quantities corresponding to them. Okay, so what we'll do is we'll try to make a connection between black hole physics and thermodynamics. This is at least a priori it should be surprising, and the reason is that black holes generally, when you write down quantum field theory or general relativity or something like that, there's no notion of temperature. The understanding is that you're always working at 0 temperature. Newton's laws by construction are at 0 temperature. Temperature only emerges if you put many of these things into one thing and you define some effective statistical quantity. That's how temperature emerges. So if you just write down the fundamental laws of nature in any context, you don't expect it to have any temperature in it at all, because temperature is an effective notion. Okay, and if you believe that general relativity is a fundamental theory, then there is no temperature in it. So that's the attitude that people took before black holes came up with thermodynamics as an essential part of black hole physics. Okay, so that's the reason why this is somehow surprising. So it says that even though you start out thinking that gravity is a fundamental force, somehow it looks like an effective, coarse-grained theory of many ingredients. Okay, so that's the reason why this is surprising. Okay, so in order to talk about this in a somewhat non-trivial setting, so you can write down black hole thermodynamics sort of trivially for Schwarzschild black holes. Okay, but I want to do it in a slightly less trivial context, and it's a very general statement for many, very large classes of black holes satisfy equations of this form, in a sense that I'll tell you in a second. Okay, but the point is, I don't want to do it for Schwarzschild because Schwarzschild is kind of trivial. Only these two terms will be there, and all of them are just controlled by one parameter m. Right? So it will not be a very interesting equation. So we want to write it for a slightly more general black hole. I don't want to make it too general, make my life more difficult. So we'll write it first for what is called, Rn stands for Reissner-Nordström. So this is a black hole with charge, electric charge. So this is a black hole with an electric charge. So not any black hole, it's a spherically symmetric black hole. Okay, so this is sort of the simplest generalization of the Schwarzschild black hole that we wrote down last time to include electric charge as well. Okay, so which means you're no longer solving just Einstein's equation, we are solving Einstein-Maxwell equation. So the coupled system of Einstein and Maxwell. Okay, so that's what we are solving. So the action for this theory, we'll write it in this form. Okay, so there are a few different choices that you can make here. So one thing you can notice is that I have extracted a G Newton here, all the way outside. So in many cases it is it's more natural in some cases to just extract it from the Einstein part. Okay, and the reason is because Einstein part is what is coupled via the G Newton to the rest of the fields in the theory. Okay, but I'm going to do it this way because this is somewhat conventional. So what it means is that you're absorbing some G Newtons and the coupling. So I also have suppressed the electric charge here. Okay, so none of this will matter for our discussions in today's lecture, so I don't want to get bogged down by these constants. But you should remember that this is a particular choice of convention, and this is a standard, it's quasi-standard convention. There is no such a very standard convention, but I'm sort of following, let's say, the conventions of this paper, which is an old paper right after the discovery of ADS-CFT by Chamberlain. So I don't know whether I think the number is correct. If it is, you can look for the word catastrophic in the title. Okay, so the authors are them, and they probably have a few papers together at the time. But the word, there is the word catastrophic is in the title. So, something and catastrophic holography or something like that. Okay, so that's the paper. So that's the notation that I'm using. So the key point here is that I've extracted a G from everywhere, and I have also extracted some E. So electric charge, etc. So the goal is basically to just make this system as simple to write down as possible. Okay? Because all of the rest of the stuff, you can absorb it. If you redefine something, you can absorb it wherever you want. So and I have set G Newton to 1. Okay, I'll bring it back periodically here and there. And that's the setup.
We just declare that it's an electromagnetic field.
Yeah.
In this case.
Yeah. I mean, the theory is, so the statement is that the theory has an electromagnetic field as well. The world has an electromagnetic field, is also part of the theory. And so the standard idea is that if you have electromagnetic field, it should couple, the minimally coupled covariant coupling to gravity, and that's the coupling.
So the field is some gauge field.
Yes, this is an electromagnetic field.
So what do we imagine? What is carrying the charge?
So right now, so for instance, you can have Maxwell's theory without electrons, right? You can have free Maxwell's theory. For instance, that is the theory which, for instance, only photons are propagating, but there is no interaction with electrons. So that's a possible universe. So I will come back to talking about where exactly the charge of I'm going to write down a black hole with an electric charge in it. And so the explanation for that electric charge cannot be found in this theory. You will have to go to some UV completion, something which some string theory or something where electric charge can be found. Okay, so note that, but that is same thing for black holes in mass as well. So the mass is also a boundary condition in Schwarzschild solution, right? I basically took out a line. So there was a question about that actually in the first lecture, one of the first lectures. I took out a line from space-time and I made things singular there. And the claim is that there is effectively, you can think of it as the analog of a delta function source sitting there. So a delta function, on the other hand, makes that, the line, you're essentially removing that line from space-time and saying that it's a boundary condition. So that's how you interpret both mass in Schwarzschild as well as mass and charge in this, this Reissner-Nordström solution, okay?
So the mass and charge is somehow
Mysterious at this point, yeah. So the idea is that, so that's essentially, you can attribute it to the singularity if you want in the space-time. And these things also has a singularity, as you will see. So that's right. So anyway, so let me define this F mu nu. So definition of F mu nu is in Einstein's theory or in any, so this is what one calls the covariant derivative. Okay, the covariant derivative means that if you have a derivative, you, instead of writing d mu a nu minus d nu a mu, which you are familiar with in electromagnetism, you make it covariant. But because the Christoffel symbols that will go into it are symmetric, this is actually the same thing as this. Okay, so gauge fields, electromagnetic fields have this property that their that their covariant derivatives or their the field strengths can be thought of as either commutators of these covariant derivatives or ordinary derivatives, because the Christoffel symbols will just drop off. Okay. So with this definition, now I can write down my Einstein equation. So which is this. So this is my Einstein equation, but not also that now I have to vary with respect to this electromagnetic field. Okay, so the gauge field A mu is my fundamental field in this for the electromagnetism, so I vary with respect to that, and you will basically find, and this is an exercise if you want to check it, it's fairly straightforward. Okay, if you have not done it, it's maybe worth doing once. Okay, so this is my equation. And this kind of comes back to the question that it was asked, which is that why is del mu f mu nu is 0 on the right hand side. There is no charge. But I will write down a solution which actually has charge. Okay, so electric charge. So this is what I'm going to do. So, yeah, and that electric charge should be understood as coming from the singularity of the black hole, effectively. Okay, so and yeah, I didn't define this T mu nu. So T mu nu is nothing but, this is the definition. I cannot go too far back, so I'm just going to tell you that this is, you can compute it like this if you like, which is that, this is the matter part. Okay, so this is the electromagnetic part. And I'm taking the, this is the definition of the stress tensor in general relativity. Okay, in fact, you can get this whole equation by taking the delta S by delta G mu nu of this whole thing. And the Einstein part comes from here, this guy, and this guy will give me some expression, which I'll just write. So which is the electromagnetic stress tensor. Okay, so if you have seen some general relativity, all of this is a bit repetitive, but we need, at least once it is good to see it. Okay, so this is my stress tensor, and the point is that the strategy for solving it is you just plug it in with some spherically symmetric ansatz. Okay, so just like you would get Schwarzschild, you would put in an ansatz for the gauge field as well and solve it. Okay, you assume spherical symmetry and then you plug it in and then go where the equations lead you, and finally you will be able to solve it. And that solution is what this Reissner-Nordström solution is. Okay, so so the solution, and you can ask, you can solve it on some software like RGTC or something. Like I think back in the day, Reissner-Nordström wrote it down by hand and solved it, but we can do it in seconds. So this is the solution. It has roughly the same structure as Schwarzschild. Where f of r is 1 minus, where instead, like previously we had m as one integration constant, now we have a new integration constant q. Okay, and but in order to fully describe the solution, I should not just describe the metric, which only takes care of this part, but I also should write down the solution for this because it's a coupled system, right? And that solution is basically A mu is minus q by r 0, 0, 0. That's the solution. Okay, so this is the metric. I could write it as a matrix, and this is a vector, so I'm writing it as a vector. Okay, and this implies that the field strength, which I can compute using this formula, is q by r square. Okay, that's the only non-vanishing component of the field strength. And FTR, which is the negative of this. Fine? Okay, so, yeah, sure. Sorry, gravitational field what? Sorry? So the gravitational field is not directly connected to the metric, right? It's basically the derivative of the metric. So it's more like the Christoffel symbol. So that will fall off like 1 by r square. So this is, note that this is not the fall off of the electric field. This is the energy of the field that is falling. So if you have a Q by R A mu, the energy, roughly speaking, it is a bit more like energy. I mean, it's not quite energy either, but it is the energy in the electromagnetic field that is sourcing the metric part. That's what this is. It's not really the same thing as electromagnetic force. So this is like, this is a bit different. This is the piece in the metric that is sourced by the energy in the electromagnetic field. That's what this is. And this is the standard metric part. And if you compute the, if you write down, for instance, geodesic equation, you can find a limit where it is Newton's law, and you can read off the force which is coming from a connection like piece, and that will turn out to be the standard Newtonian law. Okay, so that's the general setup. Any other question? So at the moment, this Q is just an integration constant that happens to show up in this Q by R because I chose some ansatz. I'm not telling you what the ansatz, etc., but nothing really changes. You can work with different ansatzes, but they will all be gauge equivalent to this solution. Okay, so if you know, so the point is this Q but has an invariant meaning, which is that you can use Gauss's law to compute its charge associated with it. So because there is a gauge field, you can compute its associated charge, right? And that is basically, so that's the definition of Q electric, is nothing but, so 1 by 4 pi is some convention, and then you have r squared d omega 2, which is the, the surface, and then you have the FRT, and this will give me, if you compute it, it's trivial, and you get Q. So that's the interpretation of, that's why we know that Q is electric charge. Okay? So,
So in the previous equation was correct.
So-
I could shift this Gaussian surface as small as I want.
Yeah.
And I was to be-
yeah, so there is, you have to be a little bit careful about going inside the horizon, but outside the horizon, So even inside the horizon, you can make sense of it, suitably, if you do it properly, because there is multiple asymptotic regions and all that. But outside the horizon, yes, it makes sense. So, okay, so it's conventional to write this guy in this form. And this is even more general. So what you do is, most of the time, these functions that show up in Schwarzschild, they will have zeros. Okay? So the zeros of this function are to define the various horizons in the problem. Okay? So for instance, in the case of Schwarzschild, 1 minus 2m by r had a 0. Divided, some function is a 0 divided by 1 by r. Divided by r. So here, you have a quadratic guy. So it is convenient oftentimes to write it in this form. Because this, the reason why it is useful is because sometimes this function that shows up here is not solvable. Or it's not easy to, easily translate it into an expression about the horizon. In this case, r plus and r minus you will be able to solve by solving a quadratic. But in general, if it is some complicated expression, you generally don't know what r plus and r minus are, at least not analytically, in terms of the parameters of the problem. And usually we are interested in r plus and r minus directly, and not so much in q and m or whatever the parameters of the solution are. So which is why sometimes people write it like this and work directly with r plus and r minus. Okay? So here, but things are easy, so we can solve, and you will see that this is the structure of my, what is called the inner and outer horizons. Okay? So r plus is the outer horizon, or this is the genuine event horizon, which defines the black hole. And then there is r minus is called the inner, or sometimes also called the Cauchy horizon. So we don't care about it so much now, but so this is the thing that defines our the event horizon. Okay, so the thing that defines the black hole. Okay, so and also r equal to 0 again is a singularity, curvature singularity. Okay. So another fact which is important for us. So this this black hole is somehow, sort of prototypical and very important for various purposes, because this black hole, see the way in which I presented it is that's a solution of Einstein-Maxwell theory, right? And so that's why you didn't have charges and so on and so forth. I mean, at least it didn't have charges in the theory, but it can arise in theories which are, like UV complete theories, like string theory, where this will just be one sector of it. So if you can always, these kinds of black holes, generally speaking, exist in most theories that are interesting in quantum gravity. Okay, so that's the reason why it's interesting. And most black holes, for instance, and many black holes which are, which one can study in string theory, where we understand all the microscopic physics, etc., all of them fall into something that are minor generalizations of this object. So that's also one reason why this is it's not just an exercise. I mean, I'm doing it right now for the purpose of writing down thermodynamics in a slightly non-trivial black hole, but it's also useful in general. Okay? So, and another fact is that this has to be the case in order for this to somehow make sense. Okay, so otherwise this thing becomes imaginary, various other things happen. So you say that what you say is that you have a if this is not if m is less than q, you typically say that you have a naked singularity. Okay, so to avoid naked singularities, so naked singularities basically means that you have the singularity lies outside the horizon. So which means that in principle, somebody who's standing far away in the asymptotic region, we can interact with the singularity, and the singularity. M square minus q square, right? So to avoid naked singularities. So this is So so that there is no completely general statement about the absence of naked singularities in general relativity, but there is conjecture. So when we cannot prove something, we conjecture it, which is called the cosmic censorship conjecture. I mentioned this, so some of these things I have already mentioned very briefly in the first introductory lecture. So cosmic censorship conjecture was first put forward by Penrose, and it has had various refinements, and it's not really, there are various violations that are known to the cosmic censorship conjecture. So for instance, in higher dimensions, and if you fine tune the initial data that, the idea is that if you collapse generic data, generic initial conditions for a general relativity and you evolve it, you will never form a naked singularity. So all the singularities that you form will be covered by horizons. That's roughly what you should take away from the cosmic censorship idea. But if you fine tune your initial data, you can actually construct naked singularities. But fine tune means, what that means is that let's say there is a one parameter family of initial value data. Okay, so let's say there is a scalar field whose profile was some Gaussian function. And you're evolving it, you couple the scalar field to Einstein gravity, and you evolve the system. Okay, and the initial condition was some Gaussian. So let's say that the width of this Gaussian, you can think of it as some parameter sigma. Okay, and as you change this sigma, there will be, for some sufficiently dispersed scalars, the scalar will just scatter off and you will not find any black hole at the end result. But if it is sufficiently small, for example, you will find a black hole that forms. So, but at the boundary between these two behaviors, when sigma, sigma is a one real parameter, right? So as you tune the sigma from one end to the other, let's say from 0 to, let's say some large value, at some particular value, you will find that there is a boundary between dispersal and collapse, and at that boundary, numerical simulation strongly suggests that you will have a singularity, okay, naked singularity. So I'm emphasizing it because this is one of the few results in theoretical general relativity which has been obtained by numerical methods, because it's a conceptually important fact which is essentially inaccessible analytically. Okay, so this is a fact which I told you just now, that there are classes of initial conditions which disperse as well as which collapse. So the boundary between them is really only accessible through numerical evolution. Okay, because numerical collapse of a scalar field is a complicated problem. We don't know how to do it, and this is in the deep interior of the solutions. Okay, so you cannot really access it using some perturbation theory or something like that. You really have to evolve it, and that is done by numerics, and this was done by Matt Chotwick at Austin back in the day. Okay, so and that's an important fact about when you can find. So the reason why it's good to remember it, because it kind of captures the philosophy that generically you never form singularities, naked singularities. But if you if you fine tune your initial data to some specific value, you can create a naked singularity. But that's just considered to be somehow some small perturbation will destabilize it, and so it's not considered to be interesting. So that's one example. But there are other examples of violations of cosmic censorship as well. But none of them, I think, basically move away from this general philosophy. I don't think none of them are sufficiently serious to say that. There is, at least philosophically, I think I would say it is correct. Okay, so the singularities, whenever they form in general relativity or gravity, typically they are covered up by horizons. Okay, so that's the motivation for demanding this. Yeah.
The mass of the black hole that forms after the collapse of the stellar.
Yeah.
In order to allow for a naked singularity, the mass should be zero. Right?
Mm-hmm.
So do you really call it
But that's okay, right? Yeah, so but even then it is not unreasonable to call it a naked singularity, because you can compute, for instance, curvature scalars. So you will find that they diverge in that point. Even if the mass is zero. So the point is, so the point is that this solution that you're getting at any finite value of m, you have a singularity, and it's covered. So it's the boundary of that m. So what happens there, you cannot, argue for without actually evolving it, right? So what you really have to do the numerics in order to make a statement about what happens at that point. That's why I said that this is one of those statements which is accessible only through numerics. Okay, so the boundary, you're correct that the transitional object has zero mass, but it is an object which is at the boundary of an object with a singularity and a horizon, right? So that's the thing that happens. So what is this precise statement about that is a question that one has to really do the calculation in order to get a conclusion to. Okay? Right. So any other questions? I'm saying that it is a naked singularity. I'm not shown it. I'm making the claim that it is a naked singularity. There is a naked singularity at the boundary between dispersal and collapse for scalar fields. No. So this is not. Oh yeah. This is not related to this observation. This is a completely different statement. This is about scalar fields coupled to general relativity with, let's say, you can do with charge as well, with electric field as well. Sorry, electromagnetic field as well. But here I'm making a statement that how you can violate cosmic censorship conjecture. So there exists one known and sort of an important example of violation of cosmic censorship conjecture, which is that you start with initial conditions which are fine-tuned so that you're at the transition between dispersal and collapse, and then you can construct a naked singularity. But the point about that is that it is a very fine-tuned initial condition, so it is not, in some generic sense, cosmic censorship is still true. And because cosmic censorship is true, I am demanding that this is the case for this black hole.
My question is just about this section.
Yeah.
Why does this mean that you will avoid me?
So I mean, for instance, let's say, so if let's say if m is, for instance, so this, for instance, you can immediately kind of see that this guy becomes imaginary here, right? So this first construction itself doesn't work in some sense. So if you go to this limit of m equal to q, what you actually find is actually an extremal black hole. Okay, so that is to find, this statement is what is really coming from the from the statement about what is it, cosmic censorship. This statement is coming from avoiding, you want it to be otherwise also, then also you will get this condition that singularity comes outside of it. But this statement is, there is a limiting statement at least you can make where m is equal to q, which is considered to be well defined. But here on the other hand, you really run into trouble. Okay, so you really run into trouble in the sense that your curvatures, if you compute curvatures, for instance, you can find problematic situations. So this is the sort of statement. So fine? Any other questions?
Q equal to 0 would be Schwarzschild.
Yeah, that's right. Q equal to 0 is Schwarzschild, and m equal to q is actually, I should actually put this here, because m equal to q is an extremal black hole which is allowed. Okay? So,
sometimes during the collapse of the scalar field, the mass starts from a non-zero value, right? Instead of a zero value.
Why is that? So, but it can disperse, right? So, yeah, it can disperse. So, the information can be contained in the asymptotic region. So, I'm talking about the mass of the black hole.
Like sometimes the phase transition is from like it will immediately start from a non-zero mass, start with a zero mass.
It may. It's possible. I didn't understand the question actually. So, I'm just talking about the situation where the initial object had no mass. So, you're starting with empty Minkowski space with a scalar field and you're collapsing it.
Sometimes the phase transition is such that the final black hole will start not from zero mass.
This is something I do not know. So I'm just making a statement about the fact that if you have a scalar field and you collapse and form a black hole in empty space, the mass, the phase transition is happening at m equal to 0. That's the statement I'm making. Yeah, certainly. Yeah. So that's the one that I know exists. I don't know whether what you're saying exists. Okay. So that is something, that I don't want to make a statement because you seem to know, you're familiar with it, so I don't want to make a statement otherwise. But I'm making a statement about the fact that mass zero black holes form and they are nakedly singular in the collapse of a scalar field, massless scalar field. There's also a massless scalar field coupled to GR. Okay, but what you're saying is, I don't know whether it is true, but if it is true, it is interesting. Okay, so yeah. Any other questions?
So what happens if the initial star has 2 greater than not collapse?
We are not considering that situation, right? We are considering the situation where a scalar field is starting in Minkowski space and we are collapsing it to form a black hole. So if you have like matter which is of the form some T mu nu, which is, in order to talk about us, so who was asking, you or you? Yeah, so if you have a matter, like if you have a star, you need to have a model for it to start with. So that model is, we want to work with this in a situation where everything is completely under control. So you want to work with a scalar field and metric and that's it. So because then you cannot argue with it. So for instance, if you write down a stress tensor, you never really know whether it is a reliable stress tensor or not. Right? So you can write down some stress tensor like, Oppenheimer's, right? Various things people have done, but none of those things are really reliable because we don't know whether they can really be. For instance, you'll have to assume some equation of state, this, that, etc. But here this is a massless scalar field and G mu nu is the metric and we believe we know what we're talking about. Right? So, and there you can definitively show, and that's what Chopwick did, that at some limit, so I'm just picked this Gaussian as an example. So because it's just one parameter, it's sigma, you can vary, but it works for various choices of initial conditions which are controlled by some parameter. Okay, so you just need, the idea is that there is an initial value space and you're moving in the initial value space and there exist boundaries of the initial value space where collapse happens. So that's the statement. Is that clear? So the stress tensor is not useful for our purposes because you could always argue that stress tensor is not physical. So here on the other hand, there is no such escape. We really have to deal with it. Any other questions? So what was your statement again? I'm kind of interested in. But can you make that statement once again?
Sometimes when the scalar field collapses, it doesn't start from equal to 0. So from non-zero, they call it type 2.
Okay. Okay. So is it, okay, I see. So is it for a massless scalar field or?
Massless.
I see. So but does it have to do with the specific initial conditions that you choose?
There is a parameter family.
Parameter what? Sorry?
The initial parameter family of the scalar field.
So it's so you were saying that by choosing the one parameter family that you're starting with, there exists different phase transitions. Is that what you're saying? That's a bit surprising. Okay. I'll talk to you after because this is something that I'm actually interested in because I think I want to talk to you. It's kind of an interesting statement. Okay, so right. So another reason to argue why we don't want horizons inside singularities. So the second reason why we don't want that is because of the fact that you expect effective field theory to break down. So effective field theory is a statement that there is high curvatures, right? High curvatures which are unhidden from everything else. High means infinite curvatures. So which means that your theory doesn't have, you can't write down, an effective field theory is a theory where you're organizing your equations of motion in terms of derivatives, okay, the number of derivatives in the problem. So if that is the case, what you expect is that, if you want to work with Einstein gravity, you want to only work with the lowest order derivatives in the problem. So, but if you have a singularity where high curvatures are present, you can no longer work with a theory with only the lowest derivatives, you'll have to include all possible higher derivative corrections, and that's called the breakdown of effective field theory. Okay, so if you have a breakdown of effect, so in order to avoid that as well, we make the statement that singularities have to be hidden inside horizons. Okay, so I think that is enough of a survey or a quick overview of the charged black hole, and with that charged black hole we can make a statement about what we wanted, which is first law of black hole mechanics. Okay, so I'm talking about mechanics here because right now the equation that I write down will become thermodynamics in a second, but right now those are equations in general relativity. Okay, so this is the reason why I call it mechanics. Soon it will become thermodynamics. So let's say if we define, so the first thing I'll do is I'll make some definitions, and I won't justify them quite yet, and I'll define two quantities. So this is called surface gravity. I'll define that in a second what it is. But let me say that, yeah, this is area we know. So I'm saying that there is an entropy of the black hole is proportional to the area of the horizon. And the second statement is the temperature of the black hole is proportional to a quantity that I'll define soon, which is called surface gravity, which is also a geometric quantity. Okay? So there are two quantities, and this is the point about these two definitions, that this is universally true for any black hole. And not just for, let's say, what is it called? Not just for the Schwarzschild black hole or the Reissner-Nordström black hole that I just wrote down. Okay? So the claim is that TdS defined in this way is equal to dm minus phi dq for the Reissner-Nordström black hole. So this is the claim. And this is, if you know how to define phi and t and s, you know, this is basically an equation that we can check directly using the parameters of the black hole. Right? So that's sort of the point here. So we have S is equal to A by 4gh cross. So let me actually write it. For the Reissner-Nordström black hole, we have T is equal to R plus minus R minus by 4 pi R plus square. So I'll show you how to define this surface gravity in a second. So you can, for the moment, you can trust that this is the case. Okay, so this is my temperature. This is my okay, so this is my the electric potential, and that you can think of as roughly as the value of the gauge field A0 at the horizon. Okay, so and yeah, so that's the rough idea. And so these quantities, so once you define the T using this, and phi is basically just the value of the gauge field at the horizon. Okay, you know, and this T is, you can compute from here. S I have defined. The claim is that this equation holds. Okay, this is just an algebraic identity relating these parameters in the case of this Reissner-Nordström black holes. So with this, what do we want? So a mathematical relation in the space of solutions of the Einstein's equations. That's what this thing is. So this holds as an equation about these guys. So let me define what a surface gravity is first, somewhat more generally. Unfortunately, this is one of those places where I'll have to assume a little bit of familiarity with general relativity. So let me first define what is a Killing horizon. Okay, so this is basically a horizon where a time-like Killing vector. So how many of you have seen what a Killing vector is? How many of you have not seen what a Killing vector is? So anybody? 2 people. Okay, so I'll give you a kind of a crash course. You can just kind of believe some things and it should be fine. A horizon where a time-like Killing vector becomes null. Okay, so this is what is called a Killing horizon, and I'll tell you what a Killing vector is. A Killing vector is basically, so So the basic point of the killing vector is basically that it's a way to characterize symmetries of space-time. Okay, so that's what makes killing vectors useful. And the equation that you have to solve in order to get them is unfortunately completely not transparent if you have not seen it before. Okay, so this is if let's say you have a space-time, and let's say there is a vector that solves this equation. So this is a short form for this. Okay, so and the reason why it is useful is because vectors can be thought of as generating coordinate transformations. Okay, and if you do the claim is that coordinate vectors that satisfy this equation result in coordinate transformations that end up not changing the form of the metric. Okay, so a coordinate transformation that does not change the form of the metric is what is called an isometry or a symmetry of the spacetime. Isometry is slightly more precise. So a coordinate transformation that does not change the form of the metric is what is called an isometry. So for instance, T going to for instance, Poincare transformations are isometries of Minkowski space. Okay, so yeah, let me give you an example of that if you have not seen it, which is that so this does not change form, remains invariant when under Poincare. Okay, so yeah, so the point is that the form doesn't change. So note that if you did if you went from Cartesian coordinates to polar coordinates, Minkowski metric doesn't change, but its form will change. It'll go from minus dt square plus dr square, whatever. Okay, but here if I do Poincare transformations, its form itself doesn't change. It remains minus dt square dx square dy square dz square. So such transformations are what are called isometries, and isometries are basically the analogs of symmetries of a spacetime. Okay, coordinate transformations change the form of the metric, but coordinate transformations or isometries don't change the form of the metric. So it's, as you can imagine, it's a specific property. So it's a special property of a spacetime that it will have an isometry. Not all spacetimes have isometries, and you can write down spacetimes which are maximally symmetric and so on and so forth, and that all those things are kind of related to the existence of killing vectors. Okay, so the claim is that if you can identify a vector which satisfies this equation, then basically that corresponds to an isometry of the underlying spacetime. Here I wrote it for Minkowski space, but you can try to look for them in other spacetimes as well. And very roughly speaking, solving those equations, this sounds like a very formal way of talking about symmetries, but the crude idea or the basic idea is that if you, let's say you have time translations as a symmetry of for instance, Schwarzschild, you know that T going to T plus constant is a symmetry, right? So that's an isometry. And you can think of Ka, so the vector corresponding to so let's say you write down a vector of this form on Schwarzschild. Okay, so this is called a time-like killing vector field. Time-like just means that this vector is time-like. So this is a time-like killing vector, which is this actually is a killing vector of Schwarzschild. You can check. You can write down this equation and check that it is actually satisfied. Okay? Note that just because it's a derivative doesn't mean that it will immediately die, because it contains Christoffel symbols. Okay, so it has to cancel, or it has to kind of die everything suitably. So you have to, when you check it, you will find that this is actually a time-like killing vector of Schwarzschild in the outside region. So what defines a killing horizon is a horizon where a time-like killing vector becomes null. So if you compute the norm Ka of this guy at the r equals to 2m part, you will see that it becomes 0, right? So that's what defines. So Schwarzschild horizon is a killing horizon. Okay, so we needed this as a prequel to talk about what the surface gravity is. Because surface gravity, so any questions on that? That's kind of like my quick flash review of killing vectors. It's fine? That's really all there is to it. Okay, so the point is that this Now I write down another new equation where Ka is a killing, is a killing vector, which is, which has some property. So I'll take a killing vector in a spacetime with a killing horizon, and I evaluate this equation at the killing horizon. Okay? So if I evaluate it, I will find there will be some number that comes up here as kappa. And this is what is called surface gravity. You can think about its intuitive meaning in terms of acceleration and so on, but I'm not going to get into it too much. Okay? So very roughly speaking, it is related to the acceleration at the horizon, very roughly. You can think about it in terms of how this is a parallel transport equation, various things you can think. But at the end, the point is that this object, roughly speaking, measures the surface surface gravitational acceleration of the horizon, and this is the way to compute it. So one thing I did not tell you is that it is very important in this calculation that this Ka, the norm of this Ka is fixed asymptotically to be 1 if you are in flat space. Because note that if it was a linear equation in Ka, you don't have to fix the overall scale. It's not. So if it's K on both sides, it doesn't matter. But here there are 2 Ks on one side. There is only 1 here. So it's important that you fix some kind of a normalization at infinity. And the standard normalization that people pick in flat space is goes to -1 at r goes to infinity. Is that okay? So that's the idea. And this is in flat space. Okay, if you are in other spacetimes like asymptotically ADS spacetimes, you'll have to normalize it suitably so that it becomes the norm of the associated killing vector in, let's say, empty ADS space. So that's what you would do if you were doing this in some other spacetime. But here, this is what, this is the norm of the time translation killing vector in Minkowski space as r goes to infinity. So that's what we are normalizing as. So once you do that, and you do this, and you evaluate this at the killing horizon, you will get some number. And I will leave it as an exercise. And since this is a bit formal, I think it's a good idea to do that as an exercise if you want to see how it comes out. So exercise. So compute kappa at horizon for Schwarzschild from first principles. From first principle means writing down this equation Kb, determining what the killing vectors are. I already told you what the killing vector is here, actually. Okay, but you can compute this covariant derivative, and then using Schwarzschild in the Schwarzschild metric, compute this guy and evaluate this there, and you should find that kappa is 1/4m. Okay. So 1/4m, or if you, it's basically 1/4gm if you are reinstating the g. Okay? Yeah. Yeah. So it is. So I did not really tell you that there are multiple examples of time-like killing vectors. This is not necessarily the time translation killing vector in the case of curved black hole. That is true. So, but what I'm telling you is that this is some time-like killing vector on the outside of the black hole, which becomes null at the horizon. Okay, so that is still true for the killing vector that you have in mind.
But killing horizon where the combination of time-like killing vector and rotation becomes null. There is
yeah, but it is still a time-like killing vector. I'm not saying that it is a time translation killing vector.
Okay.
So it's still a time-like killing vector. It becomes null at the horizon. And that quantity is enough for me to define the surface gravity. That it depends on, for instance, dynamical spacetimes it can be different. So for instance, in static, kind of spacetimes that we will deal with for all our purposes, it's all the same. So we will not have to distinguish between these subtleties. So the definition of a horizon, especially in time-dependent spacetimes, etc., is there are various subtleties. There are various things one can say. So, yeah. So, but for our purposes, for the black holes that I have written down here, this will not matter at all. So, yeah. dm plus? So, I think it depends on how you define. So, this is a Q. So, it depends on how you define this entropy. So, are you talking about doing work on the black hole? Or are you thinking of extracting work from the black hole? So there will also be a sign here related to A0 there actually. You can go check. So I think that that sign, if I have not made any mistakes, this should be correlated with the A0 definition. So I think the A0 that I defined has a minus sign, I think. So, and because of this, you know, if we follow the signs through correctly, all the signs should fundamentally come out okay. So if it doesn't, I have made some sign somewhere mistake, but the basic idea is that this is the correct first law of thermodynamics as long as I choose what system I'm doing the work on. If I think of the black hole as doing work out in, you know, or do I think of the black hole as doing work, or do I think of doing work on the black hole? So that's the difference which will cause some sign issues sometimes. Any other question? Okay, so with that, let me, so now we can, you know, so obviously, so let me do so the statement then is that this is my kappa by 2 pi and d of a by 4g. Okay, so this is the most general form of the first law of thermodynamics for black holes with charge and rotation. We haven't really talked about black holes with rotation, and we may not. I don't know whether we'll get around to it. Maybe we won't. I don't think for our purposes it's not very important to have rotating black holes. But it is nonetheless true that if you had rotations, the first law will change in this form. But note that this is the equation that you actually get from general relativity. Okay, so this is the equation that you get, and this is a geometric quantity, this is a geometric quantity, and these are all parameters of the black hole. So the important point here is that there is, at this stage, it is not clear, as I said in my first lecture, that this should be viewed as an entropy. Okay, so Bekenstein wanted to think of black holes as having entropy, and his motivation was the fact that if you throw something into a black hole, what happens to the entropy? Thermodynamics is broken. Okay, so the way he overcame that problem is by attributing an area worth of entropy, some proportionality constant which he did not fix, as the entropy of the black hole. And the reason is that there was an area theorem due to Hawking from before, which showed you that areas cannot decrease under processes involving black holes. So that was his motivation. So, and this is the equation that you get from classical GR. So now the point is that, as I told you, and as we will talk about at some point, T is equal to h cross kappa by 2 pi is what Hawking showed by doing a quantum field theory calculation of the black hole background. So here, what he did is that he fixed the factor of h cross. Okay? And that fixed this to be really an entropy of the form a by 4g h cross. Okay, so that h cross was needed because here there is no h cross. The h crosses cancel out. Okay, so here there is no h cross, but this is the reason why there is a 1 by h cross in the denominator of our black hole, basically. Okay, black hole entropy. Okay, so okay, so any questions so far? Yeah, so now comes one more GR theorem, which again we will kind of buy wholesale, is that this kappa is a constant on the horizon. On the horizon, and this is again very generically true. So note that what I'm writing here is this equation is very general, but I just demonstrated in the context of this charged black hole, in the kind of context of the Reissner-Nordström black hole. Okay, so the kappa is a constant on the horizon, is again a statement generically true for black holes on any connected horizon. If you have two separate black holes, of course, in principle at least they can be different. Okay, so, and this is what is called the zeroth law of BH mechanics or BH thermodynamics. And this is the first law. So now we go to the second law, which basically says that delta is greater than or equal to 0, which, as I said, is basically the statement that areas of black holes never decrease. So if you have multiple black holes colliding, etc., the total area at the end should be greater than the initial areas of the separate things. Okay? In fact, that puts bounds on how much gravitational radiation can be radiated from two colliding black holes. In fact, you cannot radiate more than a third, or roughly around a third of the energy in the form of gravitational radiation. So those kinds of statements are, these are all classical. So the crucial thing to note here is that these are all classical GR statements about geometric quantities on the horizon, and this particular calculation here is what reinstates it into a quantum statement about temperature. Okay? So, any questions? So we'll say one more thing and then we will close it for the day.
So the T was identified only after Hawking's calculation, right?
The which what? The sorry?
The temperature
Yeah.
was identified only from the Hawking's calculation, because from here it is not.
Yeah, so what we could have thought at the level of classical gravity is that temperature should be proportional to surface gravity, because this structure looks very similar to a first law kind of thing. And if you associate entropy is somehow naturally associated to area, because area has this no area increase theorem. So that is natural, but the relative ratio is not fixed. But the claim is that because we know explicitly what the temperature is by Hawking's calculation, then it completely fixes everything. And then we can also say that entropy is A by 4 GH cross. Okay, the precise coefficient is also fixed. Okay. Yeah. Yeah, that's correct. So you will see that this actually holds as an identity, is equal to 0. Yeah. Any other questions? Okay, so, I think I wrote it there, so yeah. Okay, so how do we? So some of the next few lectures will be about talking about temperature in the context of black holes. But let's do like the quick and dirty way of motivating that this is the temperature. Okay, and this is also, it turns out in some ways maybe this is a more deeper calculation than many other calculations that are there. So maybe what we are going to do now is in fact the right way to look at things. So to do that, so I'll give you a quick calculation. So the first observation is that thermal correlation functions. So now we are kind of shifting a little bit of gear, and in quantum systems, we can think of it as some quantum field theory if you like. Quantum systems have periodicity in imaginary time. So that statement may sound a little cryptic if you have not seen it before. So this is a statement, okay? So what does that mean? So thermal correlation functions in quantum systems are periodicity in imaginary time. This is a fact. Okay? And what do you mean by thermal correlation functions? So basically a thermal correlation function, let me call it, I'll define it this way. Okay, so this is essentially the thermal expectation value. So if you want to compute any expectation value in a thermal state means the density matrix is that of the canonical ensemble. That's what it means. Okay, so what do you compute? You basically compute e to the minus beta h O divided by trace e to the minus beta h. Okay, so that's the definition. So this is what is called a thermal correlation function. So thermal correlation function you should not be surprised by. So what I'm computing here is basically the expectation value of two fields, if you like. This O is an operator or a field, or it doesn't really matter. But the important point is that it has dependence on tau and x. Okay, so you can think of it as a field, if you like. Let me call it phi to make it a little bit. So you can think of it as a scalar field. But it's much more general. What I'm going to say is it's not even dependent on perturbation theory. Okay, it is just very, very generally true in quantum field theory or any quantum system. So, but let's think of this as a scalar field. Okay, so this scalar field, we are computing this 2-point function in a thermal state. Okay, so whenever you compute expectation values, if you have not seen field theory, if you're computing, it's part of I just chose it a definition because I kind of found that you know, the way I'm defining it turns out to have a minus sign. But this is not very important. So I'm, you know, yeah. So I probably picked it from somewhere, and the sign has gone through various things, so I didn't want to change it. But this sign is not very important, you're right. So, yeah, so this is my thermal correlation function. So, and yeah, I mean, I probably, let me actually remove it. Hopefully I will not, you know, bungle things too much from my notes, but I think you're correct that it is sort of a inconvenient thing sitting there. Okay, so what do we have? So this is my definition of thermal correlation function. So, yeah, so the point I wanted to make was that this phi t time, this 2 phi sitting here is, you should think of that as an, you know, as some operator. There are two, it's a 2-point function. It depends on one point here and another point here, right? So, but it's an operator. It's an operator that is well defined in quantum field theory, some quantum system, okay? So there are some operators separated in space and time in T and X, because this is a Euclidean correlation function, if you like. Because I'm not talking about Lorentzian time, I'm talking about, you know, this tau is a Euclidean time. Okay, and that is what one naturally is led to when we are talking about Euclidean quantum field theory, and that's the setting in which this arises. Okay, so the statement I'm going to make is that if you have a field theory in Euclidean space, and I define its 2-point function in this way, okay, thermal 2-point function. This is the natural definition of a thermal 2-point function in Euclidean quantum field theory. So the reason I'm emphasizing Euclidean is because this tau is Euclidean. As you will see, what I'm going to say will only hold in Euclidean signature. Okay? So the claim is that this object is the same thing as this. Okay? So this is what is called thermal periodicity of this. I'll show you that in a second. Okay? So this thermal periodicity is a standard feature of quantum field theory at finite temperature, Euclidean field theory if you like. And so let's show that. So the left hand side is, so this is, let me call this Z for convenience. So trace e to the minus beta h by Z. Was there a question? Is there a typo or something somewhere? It's all good? Okay. So, so this I'm using the cyclicity of the trace. So trace ABC is trace CAB, right? So I'm using that to write it this way. And then so then I'll So the reason why this happens is essentially because of the Euclidean version of Heisenberg's equation of motion, which is basically saying that e to the some tau prime, let's say, h. So let me make all of these phi's. Is equal to O tau prime x. Is that okay? So that's just Heisenberg's evolution equation. And if that is the case, then I just use this here and I got this extra e to the minus beta h. And this now is just by definition again of my thermal correlator. I have 1 by z trace. Oh, I already wrote that part. So this is nothing but GB t minus beta x. Is that fine? Okay, but that's just the definition coming from here. Okay, so note that I also implicitly assume that there is some kind of a tau translation invariance, very roughly speaking. Okay, so that also I have assumed in this calculation. So that's the reason why I am setting this to, for instance, 0, 0. Okay, so otherwise I should write tau 1 x1 and tau 2 x2. But using the time, both time and space translations, I have moved this guy to the origin and then I've kept it this here. Okay? So that the idea is basically that only the difference in the two locations matters in this expression. Fine? So the point of this calculation is that this is completely trivial calculation, but it's comes up a lot, and it's conceptually somewhat important for us. Okay, we will see that we will do this using, for instance, path integrals and so on in various ways in order to do this systematically. Okay, so and it's not quite done. Sorry. So there is one more little bit I'll say, and then we can go. So yeah, I think we have time. But the point here is that correlation functions in Euclidean time are periodic in thermal field theory. Okay? So if we can identify a periodicity in the context of black holes in the Euclidean section. Okay, Euclidean section means if you, instead of working with, so far we have always been talking about Lorentzian black holes, where the time direction was minus dt square. Right? So instead, if you are to talk about the Euclidean black holes, and if we can identify a suitable periodicity there, then we could legitimately make the case that the temperature, that periodicity beta is basically 1 over T. Oh, I forgot to mention that actually. So, but I'm sure you know this, right? Okay, so that's our basic observation. So, yeah. Right, yeah. So here, when we talk about imaginary time, we are imagining that the time is Lorentzian. So imaginary Lorentzian time is Euclidean. Okay, so this is, when we say this is just Euclidean time, it just means it's the imaginary Lorentzian time. Okay, so yeah, so it's just terminology. Okay, so what I want to do now is, if you remember from last time, let's go through this quickly. So let me give you a trick. So this is a trick that, you know, all of you who are somewhat of age are super familiar with, but maybe the babies in this audience have not seen it. So let's do it slowly. So I already wrote this actually last time when I wrote down my Reissner geometry. Okay, so this is my Schwarzschild spacetime. Okay, so and define R is equal to. This is how, I mean, I'm introducing the coordinates in a slightly different way, but it will eventually turn out to be the same. Last time I did it in full detail, but here I'm just introducing a new coordinate system R, which is a slight fluctuation around. I mean, from this coordinate transformation, it's not obvious that it need not be a fluctuation, but at rho going to 0 limit, this will be a useful coordinate system. Okay? So, and if I do that, so this means that my metric takes the form, so let me call it rho tilde actually. Rho tilde square d tilde t tilde square plus 16 m square d rho tilde square. So this is what we had last time. Okay, essentially, or you know, with up to some minor coordinate changes, etc. So this is essentially what we had last time. And now I define a new coordinate system by okay. Yeah, so if I define it like that, if I have not screwed it up, this metric should become minus rho square dt square, which is what we had last time, plus 4m square d omega 2 square. So this part is basically Minkowski space, and this part is a circle or a sphere. Okay, this is what we had. So, yeah, so this is what we had. And the reason why this is useful is because now let's go to Euclidean signature, because what we said is that in Euclidean signature, periodicity means there is some temperature associated with the system. So we can go to the Euclidean signature, and this basically just goes to rho square d phi square plus whatever, doesn't matter, Okay, where phi is now defined to be the Euclidean T. Okay, and the key observation, and this is so apart from the periodicity, apart from making things Euclidean, the one extra input is what I'm going to say now, which is that I demand that there is no singularities in this geometry. Okay, and it's note that this is basically polar coordinates in R11. So once you Wick rotate, this basically becomes R2 times S2. This was R11, Minkowski space in 1 plus 1 dimensions, and this was S2. This remains as it is when you go here, but this guy changes to R2. Okay, so but R2, it is only R2. This is a polar coordinate on R2 only if phi has periodicity 2 pi, and that's the crucial extra ingredient that we're demanding. Okay, so that's not obvious from whatever went before. So we say that phi has to be phi plus 2 pi, because if it is not, there is a conic. It's basically it's not R2. It's basically a cone, right? So cone with the excess angle or deficit angle or something like that. So this is what gives you this phi, this condition. So this is a condition that is not automatic, but we demand it. And if you do that, you basically find that by translating the coordinates back all the way, you would find that in the Euclidean time associated to the original black hole that we started with is basically where beta is 8 pi m. Okay, and this you can check is basically the same thing as kappa by 2 pi or whatever I defined. Okay, so this is essentially the simplest and probably the deepest way to compute Hawking radiation. So we will see why it is more. It's not just a trick. It's more than a trick, and this idea seems to have more traction than in many ways it should. So this was originally, I think this was first done, I think, by Gibbons and Hawking. If somebody in the audience knows otherwise, they can correct me. So I think it was done by Gibbons and Hawking. So let me give them credit. Gibbons, Hawking. This periodicity argument. So, and is there anything else I wanted to say? Yeah, so okay, let me make a couple of qualitative comments and then we'll close. So this temperature that we computed only requires, so we will see that, we will do it in a couple of different ways as well. So we'll compute Hawking's temperature in a couple of different ways. And this temperature only requires, it doesn't require a full quantization of gravity. What it requires, you will see, is basically that the fluctuations around a given spacetime, the black hole spacetime, can be quantized. And as long as there is such a consistent quantum field theory in the curved background of the black hole, then the temperature can be computed. So that's the calculation that Hawking did. And but on the other hand, the black hole entropy, for instance, there is no immediate understanding of that from the point of view of any kind of low energy effective field theory type of setup. So you basically need to have some theory like string theory in order to talk about it. And another important and interesting fact about black hole entropy, which is that it's humongous, but it's if you have a big enough black hole, big enough a black hole of the, let's say at the center of Milky Way, for example, its entropy is roughly of the order of 10 to the 88. Okay, so 10 to the 88 is a good number to remember because it is slightly less than the entropy of the microwave background, which is 10 to the 89. And it's one small hint that black holes can evaporate. So it's like basically the final stage of evaporation is not quite, final stage of systems is not quite black holes, but the evaporated radiation coming from black holes. Okay, it's very heuristic and very hand-wavy, but many times in physics, these very heuristic, hand-wavy things happen to be true. So, and the CMB has entropy which is, if you look at, for instance, the entropy of matter in the universe, it's much smaller than that of the entropy of, for instance, the black hole in the center of the galaxy. But the entropy of CMB is actually higher than the entropy of black holes. Okay, so I'll stop there. I think you can stop. Thanks.